Well, 3i Atlas seems to have made up its mind. Whatever it came here to observe, it's done watching us, and now it's heading deeper into the solar system toward Jupiter. And on December 26th, we received an update that didn't just clarify the mystery of its shrinking mass, it made this object even stranger than before. In the last analysis, the mass of 3i Atlas dropped from an estimated 33 trillion kilograms to about 260 billion kilograms. That alone was unsettling. But this new update introduces a detail that fundamentally changes how we understand what's coming off this object. Stay with me until the very end if you want to see what happens next. Additionally, if you're already interested in this, you may like, subscribe, or enable notifications at any moment. Go full screen for the greatest experience, and let's go over the recent changes. 3i Atlas is releasing dust particles that are roughly 1 million times heavier than normal comet dust. To understand why that matters, we need to talk about what comet dust usually is. When a comet approaches the sun, its ice doesn't melt the way water does on Earth. Instead, it sublimates. Solid ice turns directly into gas. Comets aren't made of pure ice, though. They're more like dirty snowballs. Ice mixed with tiny dust and rock grains frozen inside. As gas escapes the surface, it drags those dust particles along with it. In normal comets, these particles are incredibly small. Typical comet dust grains are about 1 micrometer across. For comparison, a human hair is around 70 micrometers thick. That means most comet dust is more than 50 times thinner than a single strand of hair. Those tiny particles have a huge surface area compared to their mass, which makes them very reflective. That's why comet tails glow so brightly. And because they're so light, sunlight itself pushes them. Solar radiation pressure acts like a constant wind, forcing the dust away from the sun and shaping the classic comet tail that always points outward. But 3i Atlas is not doing that. The particles coming off this object are about 100 micrometers in radius. That makes them roughly 100 times larger and about 1 million times heavier than normal comet dust. This wasn't speculation. These calculations were published on December 26th by Avi Loeb and independently confirmed by David Jewett and his team. This discovery directly explains one of the strangest features of 3i Atlas, the tail that points toward the sun. For months now, this object has displayed a sunward-pointing structure stretching nearly 400,000 kilometers, roughly the distance between Earth and the Moon. Sunward tails, sometimes called anti-tails, do exist in astronomy, but they are almost always optical illusions caused by viewing geometry. This one is not. The sunward structure of 3i Atlas has been observed from multiple angles over multiple months. It is real material moving toward the sun. Physics places strict limits on how far dust can travel sunward. For normal micron-sized particles, radiation pressure reverses their motion after just a few thousand kilometers. Avi Loeb calculated this limit precisely. The observed tail extends more than 100 times farther than that limit allows. There is only one way to make that possible. The particles must be much larger and heavier. Particles around 100 micrometers in size have enough mass that sunlight cannot immediately push them back. They can coast toward the sun for hundreds of thousands of kilometers before radiation pressure finally overcomes their momentum. That conclusion isn't optional. It's enforced by physics, but this creates a new problem. How do you eject particles that massive in the first place? David Jewett's team calculated the ejection speeds required for different particle sizes. Normal 1 micrometer particles are ejected at roughly 22 meters per second, but 100 micrometer particles reach only about 2 meters per second, 2 meters per second is walking speed. That is incredibly slow for cometary material. And yet, it is just barely fast enough for those particles to escape the weak gravity of a small nucleus and drift sunward. This ties directly into the mass mystery. Earlier in the year, observations suggested 3I Atlas was at least 5 kilometers wide. Later measurements, especially those from December, indicated it was closer to 1 kilometer. At first glance, the discovery of giant dust particles seemed like it might explain the discrepancy, but it doesn't. Not directly. The 1 kilometer estimate comes from measurements of carbon dioxide gas escaping at high speed. That calculation deliberately excludes dust of any size. Tiny dust or giant dust doesn't affect that measurement at all. The 5 kilometer estimate came from something else entirely. It was based on the complete lack of detectable non-gravitational acceleration earlier in the object's journey. If material is escaping and you don't see any push, then the object must be extremely massive. That's where the larger size estimate came from. So here's the subtle but critical point. 3I Atlas may have been losing enormous amounts of mass early on, but it was losing it in the form of extremely slow, heavy particles. Because those particles drifted away so gently, the resulting acceleration was below detection thresholds. The object looked massive because it behaved massive. Later, closer to the Sun, scientists finally detected non-gravitational acceleration. That's when the mass estimates collapsed. And this is where Avi Loeb's most provocative idea enters the picture. What if those giant particles aren't rocky dust at all? What if they are chunks of ice? This sounds strange because we've never seen anything like this in a comet before. But the composition of Thatch 3I Atlas makes it plausible. Observations from the James Webb Space Telescope revealed that this object is about 87% carbon dioxide ice and only about 4% water ice. That is the opposite of normal solar system comets. Carbon dioxide ice sublimates at much lower temperatures than water ice. As 3I Atlas approached the Sun, carbon dioxide would begin sublimating first, producing powerful jets of gas while water ice remained solid. Those CO2 jets could be strong enough to rip chunks of water ice from the surface and carry them away. Carbon dioxide gas escapes quickly and is easily pushed by sunlight, forming a conventional tail. But the water ice fragments are heavier. They don't respond to radiation pressure as easily. They keep moving sunward, forming the observed anti-tail. In this scenario, the carbon dioxide drives the activity, while the water ice becomes ballistic debris. This single mechanism could explain both anomalies, the massive dust particles and the dramatic change in inferred size. 3I Atlas isn't shedding dust the way normal comets do. It's shedding structure. Whether this makes it an exotic natural comet or something even stranger is still an open question. But one thing is no longer in doubt. This object is not behaving like anything we've seen before. If you made it to the end, I appreciate you being here. Drop a like if this stretched your intuition a little, and let me know what you think this object really is. Happy holidays, and stay curious.